that should
Okay.
work.
That's great. So next up, we have Lorenzo Cocco, who is a fellow PhD student here at the University of Geneva. I think he has the unique honor of being the only non-Aristotelian to speak today. So I thought we needed to not just be a self-congratulatory crowd, but rather have someone pushing us a little bit from the outside. And hence, I wanted to invite Lorenzo, since he's working on very much on these questions. So please, Lorenzo.
Well, thank you very much, Ryan, for inviting me. And first of all, apologies for my voice. I hope it will carry me through. So as Ryan said, I am by no stretch of the imagination an Aristotelian, either in spirit or in character or in method or in anything, maybe quite the opposite. So I suppose the plan was to use me as a foil, I guess, for the views to be discussed in all the other talks. Ryan has suggested the title, because I tend to choose my own devices, very, very boring ones. But the views I actually want to defend is the following. According to our best physical theories, mathematical facts either cause or metaphysically ground purely physical facts. As a corollary of that, again, according to our best physical theories, I will argue that mathematical objects have causal powers or are ontologically prior to physical objects. Now, I will not defend that every mathematical object has causal powers, or that every fact, mathematical fact, causes some physical fact. If you ask me, what does 2 + 2 = 4 cause? I might say nothing that I know of. There will be only some very specific ones that I think do have causal power, at least according to our theories. I keep emphasizing according to theories we have now, because I will not argue that they in fact have causal powers or that do ground things. It may well be one of my research areas is on the program of nominalization of our field, and I think if the program succeeds, then we will have version of our theories according to which this is not true. But my thesis is that take any version of our physics that we have now, and you will have this conclusion. So to understand what the view is, consider this very popular passage in Mark Balaguer's book, Platonism and Anti-Platonism, about mathematics. When he says that science does not assign any causal role to any mathematical entities. Thus, it seems that empirical science predicts that the behavior of the physical world is not dependent in any way upon the existence of mathematical objects. So in the earlier sentence, he just talks about causation, but in the second sentence, he enlarges it to any notion of dependence. And the usual thought, or the main motivation for fictionalism would be the view that, well, what this suggests is that what science says about the physical world could be true in some sense, even if there weren't any physical objects at all. Now take that passage. What I want to argue for is exactly the opposite. That is that if you take physics at face value, what it does is say that mathematical objects are not isolated, or that not all of them are isolated from the physical world. So the main assumption that I will assume, I will make at the beginning, and I will use again and again, that I will assume that the program of Hartree field to write down what he called nominalistic and intrinsic version of our theories cannot succeed. For example, let me suppose it cannot be applied to general relativity. I will proceed like this. I think that Balaguer's claim is very, I think, very hard to maintain. Just to begin with, if you just take physics very, very naively, especially the most rigorous mathematical physics we have, it seems not true that if you take just prima facie what it says will conform to anything like what he says. So suppose you open the quantum field theory textbooks, what we will be told basically is you will start from some sort of classical field described mathematically, you will quantize it, you will get to some Hilbert space with observables defined on it, and then you will define particles or physical objects from these algebra of observables. There will be maybe some states, some what they call excitations of the state, and you take it literally. What you will do is start from some purely mathematical objects, and at some point you seem to transition into identifying them with physical objects. Actually, Tim Maudlin has a very, very nice and much more basic example of this point when he says that mathematical physics uses mathematical structure to represent physical states of affairs. Unfortunately, the distinction between the representation and the entities represented is often elided in the common manner of speech. And he has this example, which I think is pretty characteristic. So as a simple example, take the term scalar field. It would not sound in the least odd to say that the X field is a scalar field. Famous scalar field from the Standard Model, right? Further, if one inquires what a scalar field is, it would not be at all out of place to be told that a scalar field is a mapping from space-time points into a set of scalars. It has either real or complex numbers. Other way, definition of what a scalar field, you might be told, well, it's just a function from space-time points to numbers. However, if we naively put these two innocuous statements together, we appear to get the result that the X field, which took to be a physical item, is a mapping from space-time points into the field of number, which is an abstract mathematical object. Now, I think that physics is just full of this kind of thing. So the example I was given earlier is when you're told that, oh, a particle is an excitation of a quantum field, and you're told, oh, what is a quantum field? Is an assignment of an algebra of operators to space-time. That's what the definition in the textbook will say, or would be a sequence of Lagrangian density, whatever, some mathematical objects. Now, I will not rely on this. So my argument is, I will not rely on this. What Maudlin says is, oh, this must be a confusion. I actually don't think that it necessarily is a confusion. I think there is nothing wrong with just making this identification. But what I will do is assume for the sake of the argument that we ought not to make such identification. We should go through physics with a tooth comb and try to always distinguish what is mathematical from what is physical. So the idea is, let us assume that it is possible in principle to have a formulation which sharply distinguishes mathematical objects and mathematical properties from physical objects and physical properties. What I want to show is that even then, there is what I take to be a strong argument that mathematical objects will either cause or ground the physical facts, at least some physical facts. So let me proceed. So how should we present a physical theory to make clear, to make a sharp distinction between what is physical and what is mathematical? Here I will take a suggestion that I take to be some often commonly made, both in the philosophy of physics, for instance, by Maudlin that I was citing earlier, but also in the philosophy of mathematics. Philosophy of mathematics, this goes through the name of the mapping account of the application of mathematics. The idea is something like this. Suppose that a physical theory, at least presented canonically in a way that is not confused, will consist, say, of a description of some mathematical structure together with what some call a commentary. What does the commentary do? Well, it tells us what the structure represents. The analogy is often made is a mathematical structure is like a map of a territory. The physical universe is a territory, and there is a map, and there is some sort of correspondence between the map and the territory it describes. I will use the following terminology. I will call, well, whatever is represented, the physical thing, I will call that the system, and the mathematical structure is the model. What does a physical theory do? Well, it describes some mathematical model, and then it tells us how or what it represents. So how could we do a very simplified example of what it would take to present a theory like this, which I take to be the most favorable to what some call the Eleatic principle. That is what Balaguer was defending earlier. could we present, say, general relativity like this? So the example that I did in, say, in the paper goes with this was already simplified. I'm already simplifying what I did. I would just ignore, say, matter fields and just concentrate on space-time. But suppose I did something like this. Take general relativity to be the following. Well, first you postulate some purely mathematical axioms that some structure exists. The structure that you need will be called the semi-Riemannian manifolds. So the stuff you get by adding to a smooth manifold a metric that tells you distances. Then you need to specify, okay, this is the mathematical part, then specify what is exactly in the world to be represented. And here you could say, well, what is to be represented by the manifold is physical space-time. There will be a collection of points or regions which the points can be fused together to form region. There is what we call a mereology, right? Some of these will be geodesics, and there will be primitive relations between such physical objects. For instance, a relation of congruence, as we have in ordinary geometry. We could say, well, these two segments in space-time, they are congruent if they have the same length or
Lorenzo, you're muted.
well, it says that you muted me, so I was wondering if I said I had already.
Sorry, not sure how I did that. My apologies.
I said something too un-Aristotelian. It was too much. So the example was, well, we need to specify what is in the mathematical universe, what mathematical structure we need, and then what we take to be in the physical universe. But to have a theory, what we need is then an account of how we represent, how the structure represents what is in the world. Suppose that we can do it like this, which is the only account I have what representation could mean. What we might say is, well, that there is some correspondence between the physical things and the mathematical things that represent them. For instance, you may imagine that the points of space-time, the physical points or events, correspond to points of the manifold, the mathematical points. If you take another example, you might think that, say, the gravitational field, which is a physical object, is represented by the metric field, which is a tensor, a mathematical object. Or you might think that a quantum state or particle or something like that is represented by a wave function, which is a mathematical object. Or you might think that the electromagnetic field is represented by a vector field, which is a mathematical object. Again, you have a correspondence, you have a function that tells you, okay, what an impure function, what we call, that picks some physical objects and tells you what mathematical thing represents it. Here it be between points, physical points and points of the manifold. And you can extend it to regions. And the idea is, well, the structure represents because we postulate, the theory postulates, that whenever some physical relation, so for instance, congruence holds between the physical objects, some corresponding mathematical relation holds between the representatives. This is just a generalization of what you do, say, in analytic geometry, when you have a Cartesian frame and you associate points to triple of numbers, and then geometric property like being a circle are transformed into equations. Well, suppose physics is like that, or at least it could be formulated always in such a clear fashion. What I want to argue is that even then, from this description, you would have reason to infer that the mathematical object influence the physical ones. Why? Well, as an analogy, let us go back to something you have been probably discussing all day, like the Benacerraf problem. And consider the version in which the maestro Hartree Field puts it in his 1989 book, the Mathematics and Modality. It's a very brief passage in which he puts it like this in terms of explaining the correlation between the mathematician beliefs and the mathematical facts. So this is the formulation. It says the idea of this version of Benasserov problem is that there is a correlation between the mathematician belief states and the mathematical facts. The idea is, well, the correlation is that in general, when mathematicians believe that P, then P. And that, he says, is so striking as to demand an explanation. It is not the sort of fact that is comfortably taken as brute. So the Platonists can postulate, he says, brute facts, say the axiom of set theory or purely mathematical axiom, but he says that special reliability relations between the mathematical realm and the belief states of mathematicians seems altogether too much to swallow. He has this final analogy, where again he stresses the idea of correlation. It is rather as if someone claimed that his or her belief states about the daily happening in a village in Nepal were nearly all disquotationally true, despite the absence of any mechanism to explain again the correlation between those belief states and the happenings in the village. So the argument, if you reformulate it, could be reformulated as, well, the Platonist postulates a correlation between the beliefs of mathematicians and facts about the mathematical universe. Well, but if there is no causation, the Platonist has no explanation for this correlation. Therefore, basically, well, we should deny Platonism, something. This is how he puts it. And now this argument has been, of course, enormously criticized in the last 30 years. There have been many solutions. For instance, one might say that the correspondence is at the end a coincidence, because the mathematical universe is so vast that no matter what we would have believed about the mathematical universe would have been right. Therefore, we could not have been wrong. This is what's sometimes called plenitudinous Platonism. Another attempt to solve the problem is to say, well, actually our mathematical beliefs are constrained by evolution. Therefore, well, we can explain why we have the beliefs we have. And since mathematical facts maybe are necessary, well, we can explain why they two line up. Another challenge has been, say, forwarded by John Burgess, was that in what sense is it a correlation? And I think that all of those are pretty good replies. So always my strategy is to start from a bad argument, but which has something intuitive, and now formulate a good argument. I think that in the vicinity of that argument, or again, just sticking to the idea of correlation, there is actually an argument that is much harder to refute. So go back. So here is the structure of the argument I will give. Premise one is, let's turn to this idea of models and systems. Well, what we have told before, what the physical theory says, in the list presented canonically, is that there is some sort of mirroring between a model, say a semi-Riemannian manifold, and a physical system, say the solar system or the space-time in the solar system. That, I think, is a case of a vast set of correlations between two things, in a very obvious sense now. For instance, if whenever on the physical side, whenever the curvature is zero, you will have on the mathematical side that a certain mathematical object, the Riemann tensor, is zero. So whenever space-time is flat, let's put it not, whenever space-time is flat, the Riemann tensor is zero. And whenever the Riemann tensor is zero, if you look at the corresponding object, the space-time is flat. So this is a type of correlation that is very similar to, say, the correlation between a switch and the light. Whenever the switch is off, light is off. Whenever the switch is on, light is on. You have clearly the type of correlation that invites causation. And in fact, a question of causation or of ground, as we say. So the premise number two is the following, which I take to be implicit in Phil's discussion. Take any correlation between two or more variables. Well, that is either a coincidence, or there is some common cause or ground, or it is the result of some dependence relation, which you might say is either causation or ground, from one of the variables to another. I talk of ground because this is often neglected in this discussion of correlation, but actually you have sometimes correlation that are explained by constitutive rather than by causal relation. For example, there is a correlation between the weight of my hand and the weight of my total body. That is not because the weight of my hand causes the weight of my total body, but because it partly constitutes it. So I will formulate it as either a coincidence or some confounding factor, as they say in statistics, a common cause of ground, or there must be some dependent relation going in one of the two directions. This is the premise number 2. Now, the third premise I will try to defend is that the correlation is not a coincidence. So unlike in the case of the correlation between the beliefs of mathematicians and the mathematical universe, there is no good argument, or there is no way to show that it is a coincidence unless the program of arc field works. This is why I would need my assumption. The fourth premise is that there is no common cause ground. And finally, the last thing that we need to show is that the physical facts do not cause or ground the mathematical facts. We agree that if you grant me 1, 2, 3, and 4, I will conclude that there must be some causation or some grounding going one of these two directions. And the last step would be to argue that, well, it cannot go from the mathematical facts to the physical facts to the mathematical facts. Therefore, it must go from what I would call Platonic causation or Platonic influence, going from mathematics to the world. Once we have all of that, then of course it follows that mathematical facts either cause or ground physical facts. All right, let me briefly defend the premises that I think are more controversial. Well, the correlation is not a coincidence. Why do I think that? Well, in one sense, it is kind of obvious. So if you take a typical example of a coincidence, recently, we're much discussion about the fact that in the last 10 or 20 years, every team that won the Champions League had a Croatian player on their team. This is a typical example of a coincidence because, well, we do not think that it actually is something that we will project in the future. And in fact, it was falsified just now because Manchester City won and they didn't have a Croatian number 12. The kind of thing that we do not expect. Coincidence is something we do not expect to hold in the long run. Whereas the correspondence between the physical system and the model, in the case of general relativity, is nomologically necessary. So it cannot be a coincidence in that sense. Now, could it be a coincidence in some other sense? Maybe yes. For instance, you might imagine that you have my watch and a pendulum. They both are harmonic oscillators. And it intends to be correlation between the position of my watch or the position of the needle on the quadrant and say the position of the pendulum. The two do not interact causally or from ground, but there is a correlation. Why? Well, maybe because they just obey very similar intrinsic laws that determine their behavior separately, and it just happens that by coincidence they are similar, therefore they would be correlated. Something like this is possible, but the crucial point is that if the program of arc field is not possible, then we do not have an independent explanation of the regularities of the physical universe. There cannot be a similarity in the intrinsic laws that govern the physical universe and the mathematical model because there are no intrinsic laws for the physical system. Now, why there is no common cause or ground? Well, here the reason has to do, I guess, with theology. So maybe it is the one audience where the possibility of God having established a sort of established harmony between the physical system and the mathematical model will be taken somewhat seriously. I think that if you are ready to buy that picture, and many are not want to meddle theology with philosophy of mathematics, but if you accept that picture, I think it's much easier to just consider that mathematical objects are ideas in the mind of God. So you would just have the influence again from mathematical objects to the physical ones. Finally, why do I think, and this is the last point I want to make, the crucial part, we have established there must be, if the argument is sound, some either causation or ground in one of the two directions. Why do I think it is the mathematics that causes the physics and not the other way around? Well, Here I will give two brief arguments, but the stronger one goes to the following principle, which I take to be very plausible. It says that whenever there is a correlation, which is due to say, let's first take the case of causal interaction, the direction of causation will go from the variables that we can independently account for to those we cannot independently account for. So what do I mean? Illustrate this with the example of, say, a portrait of my face and my face. Suppose a portrait has been made of my face. Why do we think that the causation goes from facts about my face to facts about the portrait and not the other way around? Well, because in principle, I can explain facts about my face. So why is my nose so long? Or why is it between my ears? These kind of facts. You can explain it by genetic without ever mentioning the picture. Whereas we have no causal explanation of how the picture ended up being, or the portrait ended up being how it is, without mentioning my face. We just do not have such an account. The same goes for, I don't know, if you have an orchestra and they follow the musical score, you can explain why the score has been written as it is without mentioning the orchestra, or at least you can mention just be the intentions about the orchestra, but not with the actual playing. Whereas you cannot explain what the orchestra is doing without mentioning that where they have taken the score from. So again, these principles seem pretty solid. What does it entail in our case? Well, we can explain every regularity we want about, say, Schwarzschild spacetime, the fact that it satisfies these or those mathematical properties in pure mathematics. We do not need physics. The axiom of set theory will entail nearly all the relevant properties. What is that we cannot explain independently of mathematics? It is the physical regularities. We cannot explain why the planets go on elliptical orbits without doing mathematics, or we cannot explain, say, to pick a more proper example, we cannot explain, say, the properties of black holes without using mathematics. Again, the assumption is that Fields program doesn't work. Again, I just need that again. All right, this was the first argument. Very quickly, the second one is that, again, if Fields program doesn't work, what we want to do is, as I just said, explain the physical regularities using the correspondence. That was the physical postulate that we use to explain physical regularities. Therefore, we cannot use the physical regularities to explain the correspondence. Otherwise, we will be going into a circle. You will ask me, it will be a case which you ask me why P, and I say Q, and then you ask me why Q, well, because of P. That some people believe that if there are different types of explanation, the circularity is not problematic. I have not been able to understand this piece of philosophical sophistry yet. But to conclude, if you grant me the 5 premises I needed, we get that mathematical facts cause or ground physical facts. Thank you very much.
Well, thank you, Lorenzo, for holding our feet to the fire. We have a perfect 15 minutes for questions. So, Eduardo, looks like you're first up.
Thank you very much. I very much enjoyed your presentation, Lorenzo. Thank you very much. And you reminded me of a couple of things. One is a commentary on the Metaphysics of Aristotle, that St. Thomas, where St. Thomas says that mathematicals neither set other things in motion, nor are they set in motion. Right? So there is no, they are not a cause in the sense of an efficient cause, but they could be in some other way, right? And the other thing that reminded me of, and this ties back, by the way, to the earlier presentation by Ryan, is a distinction that Aristotle makes in Book 4 of his Physics between the number, or that by which we number, the number by which we number, ho arithmumen, and numbered number, the thing that is numbered, to arithmumenon. And he says that, well, St. Thomas explains this text a little bit further and explains how the numbered number is, for instance, 2 dogs, 2 men, etc. Things that exist in reality, whereas the number by which we number is absolutely taken, and it exists only in the intellect, in our understanding. And of course, the interesting thing here is how one can be the cause of the other. And there are two ways in which this can happen. In the artificial order, if I create a chair, I can decide how big or small it is, or how many chairs I'm creating. And in the natural order, it's the opposite. My knowledge of how many things there are, or how large or small, comes from the things themselves. So I found very, very interesting your presentation, and also that you consider causing, that mathematicals are either causes or grounding. And when you say grounding, I take it to be some kind of principle. Of course, all causes are principles, and this would bring us back to the Aristotelian, to the diverse Aristotelian modes of being a cause. And of course, the Aristotelians would claim that this is some kind of formal causality. So I was wondering, in what way would you say that these are causes, or if not a cause, meaning mathematicals, they should at least be principles in some way. So what is that way that you consider they should be causes or principles? Thank you.
Yeah, that's a good question, because I think what the argument shows is that there is some sort of dependence relation of some sort. And I have tried to cover the possibilities by saying either some sort of causation or some sort of metaphysical ground. But these are very, very broad terms. So what kind of causation would it be, and or what kind of ground would it be? Well, I think the short answer is that I don't know. But I think that when you move further from efficient causation and you consider other Aristotelian notion of causation, they seem to me more similar to what other people would call ground. So the answer is that I am not sure. I actually would not exclude, as you do, the idea that it's just efficient causation. It's just exactly the same thing as same type of causation that when I turn the switch. But I have no arguments for either option.
Thank you.
All right, I don't see a hand, so I'll exercise my chair's privilege, Lorenzo, as if I don't hassle you enough. But so I wanted to push you a little bit on an analogy. So let's take energy. So energy is also something that, we would say that we kind of discover somehow by looking at nature, right? But it's not like a separate thing. So it's not as if like there's the ball of energy over there that's causing stuff to happen or whatever, right? It's just kind of a principle that's of the things we already see, that they have a certain kinetic energy, a certain chemical potential, certain gravitational potential, what have you. And yet, we often find it most convenient to kind of discuss physics by explaining things in terms of the energy, right? So we say, well, it's because the kinetic energy transferred was such and such that the ball left with such and such a, velocity, acceleration, whatever, right? So it seems like we tend to use it as an explanatory element, and often it's one where, it kind of has this role in physics, and yet, and in some sense, I guess you could say, well, it's playing some kind of causal role. I don't necessarily want to completely exclude that, but like, it's not clearly a causal role in the way that like things play a causal role, because there isn't some extra kind of like stuff in your, thing in your ontology called the energy, which is doing X, Y, and Z, right? So it seems like this should be at least a little bit analogous to the Aristotelian response to your five, right? So the way that physical facts would cause or ground the mathematical facts would be in the way that physical things have certain energies and exhibit certain symmetries and transformations. Yeah, so I guess what do you think of that analogy, or would that be a way? Yeah, just go ahead. Sorry.
Yeah. I think that we have like different questions here. So one theme that you seem to touch on is the idea that energy should not be conceived as some sort of thing out there. over and above the physical objects and their various interactions and the rest. Well, that seems to suggest the view that, first of all, well, it's not the kind of thing we would quantify over. There's not some sort of stuff that we wouldn't quantify over bits of energy. It would just be a property of physical systems that you can assign a physical system, and you can often define for physical systems. And in that sense, I would say they're just as real as anything else. If you have the energy, if something is an energy eigenstate of something and it has some definite energy, I think they're just as real as saying that it is red or blue or whatever, just a real physical property. That would be the answer. Of course, it's not sort of stuff, but that's just because it is in what we call the ideology rather than the ontology. So, but I don't think we can make the same move for tensors or quantum fields or for these kind of things. That's what this analogy I see.
Could you just say 1 second why you think we can't make that move for tensors or whatever?
Well, because at least maybe I should rephrase and say that I do not see how we could make that move. So I have an idea of how we might introduce by definition or define various notions of energy, and it would just be a predicate that applies to things. So there is no extra thing. Whereas I have no idea how we could reduce mathematics, or at least what we would do is just do the program of Hartree field, I guess. I mean, there is no middle ground there, as I see.
Yeah, I'd be interested. We should talk sometime about in what sense the field is a nominalist. But anyway, Timothy, I think you wanted to get in. Got time, so.
Yeah, thank you. Sorry, I was a little bit late coming to yours, Lorenzo. But I want to ask one question that maybe you clarified earlier or would otherwise appear resolved from some other considerations that I'm not attending to, but it seems like there's a parallel with language here. And I don't know that this would count as an objection. Maybe it would. I haven't thought through it enough, but and if we kind of run the argument you've given here on your shared screen with language as the principal thing being described, so we would conclude, or yeah, I'm not quite sure where it would fit in there, but it just seems like there is this thing that language describes, obviously, and signifies. It's not a coincidence. It's not like there's a cause for why, at least in a certain sense, an exact cause for why we call, say, a book, a book, a book, in English. So I don't know. I'm just wondering if you see a parallel, or if you care to comment on it, or sorry that this is a little bit half formed, but anyway, thanks.
No, I think it's always interesting to try to take other examples. So I use I don't know if you were here when I made the map example, but the analogy would be, well, mathematical structure represent like maps. Well, maybe they also represent like pieces of language, although I think here the representation is different. I think the analogy with maps is stronger because in a map we have some relations between some dots, right? And the idea is, well, do we have a one-to-one map between the dots and the objects? And then in language we do not have that. I think it's a different type of representation. Nonetheless, it's still a form of representation. And we could ask, well, how does that work? Here, my suspicion is that, well, we can give a straightforward causal story for why the representation holds, but it won't give any extra special powers to words. It won't give them the power to affect what they represent. It's not because I utter something that magically that happens. I think that when we can, of course, it would be a complicated story, it would be an interesting story of why we say what we say, but it would be, I think, it should be possible to explain, say, why we utter what we say as a response to our environment, or just because, well, we like to think what we think. And it won't require. We could explain the correlation that is starting from the world to language, and then language to world. Because although we use language to represent the world, that's not what we postulate. So the crucial difference that physics does not say, oh, well, as my basic premise that there is this relation between language to world. Well, just uses the representation. So I don't think that there is any analog I could make to defend 5 as I do in the mathematical case. So my argument breaks down at 5, I think.
All right, well, let's thank Lorenzo again for keeping us from either mere back scratching or backbiting, and thank you. All right, and we will be back in 15 minutes for Emily Katz, who's going to bring us, the talents of a real historian instead of us fakers.